Hey everyone. In this video, I'm going to talk about estimation and uncertainty in experiments, right? So in previous weeks, we didn't only talk about survey sampling and estimating population proportions based on surveys, but we also talked about a couple of different studies that included basically randomized controlled trials, where we had some intervention that was randomly assigned to a treatment group and not to a control group. And we looked at the causal effect of that intervention by comparing the treatment group and the control group, right? But whenever we kind of examine these differences, we also wanted to know to what extent these differences could be just due to chance, or to what extent they truly represent kind of a systematic causal effect of our treatment, right? So ultimately, this kind of brings us to, rather than only examining the uncertainty in a population parameter, as in the previous videos when we talked about population or survey sampling and inference based on survey samples. But we're actually comparing now two different groups, and that's ultimately much more interesting for us in order to answer kind of causal questions, right? So we could think of this in terms of comparing public opinion differences across groups, or as I mentioned, differences between treatment and control groups in experiments, but also in natural experiments, or one of the examples that we're going to look at are going to go back to the difference in difference designs, where we have again a comparison between a treatment and control group that was not based on a true randomized control trial. Okay. And we're going to focus on this again, kind of in the context of repeated sampling and repeated data generating processes. But keep in mind that in the book, there's also a section that talks about estimation and kind of estimating uncertainty around causal estimates based on the randomization procedure itself, right? This is what is called randomization-based inference, where we basically consider the uncertainty based on different possible treatment assignments and examine to what extent the treatment assignment basically led to, like just by pure chance, led to an imbalance that ultimately resulted in the treatment effect, right? So this is an alternative way of characterizing the uncertainty around our causal estimates in the context of randomized controlled trials. But here we're going to focus on, again, kind of this large sample argument and kind of this repeated sampling argument rather than a randomization-based inference. But make sure to check out the section on randomization-based inference as well. Okay? And the way we're going to do this now to kind of move to inference in experiments, or more generally estimation and characterizing uncertainty in experiments, is we're going to go back to two examples that we talked about before. The first one being the social pressure experiment, and again, just to reiterate what this social pressure experiment was about. This was an example of get out the vote messages that were delivered in the context of the 2006 Michigan primary, and those were a couple of different mail-in interventions where people were either reminded that they're being studied for turnout, and the social pressure treatment particularly gave people information about how their neighbors voted, and also indicated that after the election there will be another mailer indicating whether that person voted or not. And the control condition, of course, was people just didn't receive any mailer whatsoever, right? And the goal of inference was to see whether these mailing interventions increased turnout in those specific neighborhoods. Okay. And so just to reiterate, in when we looked at the point estimates in this setup, we looked at the turnout rate in the primary, and we compared ultimately the turnout rate in the treatment group, which was a point, and this is now focused on the social pressure experiment part, not on this Hawthorne treatment or the social duty treatment. We're focused just on the social pressure versus control. The turnout rate in the social pressure treatment group was around 37%, and in the control group was around 30%. The sample size in the treatment group and in the control groups were 360 and 1,890 respectively. And this is all kind of revisiting what we talked about in the past. We estimated our average treatment effect for our intervention as the difference between the average turnout rate in the treatment group minus the average turnout rate in the control group. So that's 0.37 minus 0.3. So that's an average treatment effect of 0.07. Okay. Now the next step is, but of course the question now is, how much uncertainty is there around this estimate, right? How certain can we be that this estimate is, not just due to chance, but actually kind of represents a systematic causal effect of our intervention. And again, we will look at this from the perspective, kind of from the same perspective, we're using the same arguments that we used in the context of survey sampling, which is basically asymptotic. We use the asymptotic properties of our estimators to kind of characterize their sampling distributions over hypothetically repeated sampling to then describe the uncertainty and average deviation across these repeated data generating processes, across these repeated sampling procedures, in order to provide an estimate of the uncertainty around that average treatment effect. So what we're going to do is we're going to compute the standard error around this difference, okay? And the way we compute the standard error is we have to look at, of course, it's the variance in the difference between those two x bars, and the variance of that difference is of course equal to the sum of the variance, and so we have here our variance xt bar minus times 1 minus xt bar divided by nt for the sample size of our treatment group, and the same variance for our control group. And of course we divide again, that's kind of the same logic, we would divide by nt and nc to since we're looking at the deviation across or the standard deviation of our sampling distribution. So this is not the standard deviation of our xt or xc, this is the standard deviation of xt bar and xc bar across hypothetically repeated sampling procedures, right? That's what the standard error describes. It describes the uncertainty around repeated sampling. We plug in our sample sizes and our proportions, our xt bars and xc bars, to get a standard error of 0.028. And again, this standard error is the average deviation in our, in this case, the average treatment, the estimated average treatment effect across repeated samplings. Okay. We can then, based on that, using the same arguments that we had in the context of sample surveys, just let me, move myself up here again. We can compute the 95% confidence interval based on the central limit theorem, so based on the asymptotic properties of our estimator, by subtracting and adding 1.96 times the standard error in both cases. So that's 0.07 plus minus the standard error, which is 0.028, times 1.96, which is the critical value for the 95% confidence interval, to arrive at a 95% confidence interval of 0.016 and 0.124. So again, 95% of those confidence intervals over repeated sampling procedures would include the true population value. Okay, so given now this confidence interval, we can be fairly confident that that this average treatment effect is truly larger than 0. This is not just due to chance. This is actually a non-zero causal effect that we estimated here. Okay, so this is based on, or this is now the example of the social pressure experiment. We can go through the same logic in the context of the minimum wage study that we talked about in previous videos. And remember, this was now not a randomized controlled trial, but rather a natural experiments where we're comparing basically New Jersey and Pennsylvania in terms of their employment rates after the minimum wage was raised in New Jersey but wasn't raised in Pennsylvania, right? And we looked at 3 different identification strategies in this context. We looked at the cross-section comparison, so looking at New Jersey and Pennsylvania after the minimum wage was increased. We looked at the before and after comparison, just focusing on New Jersey and examining whether the increased or decreased employment. And we talked about the difference in difference design, or the difference in difference analysis in this context, where you look at the change in Pennsylvania versus the change in New Jersey before and after the minimum wage was increased. Okay, and now the question is, how should we calculate the standard error under each strategy, right? How can we quantify the uncertainty under each of those conditions? Okay. Then of course the next step, how do we compute the confidence intervals in each of those scenarios? Okay, so let's jump right in. The first thing we're going to do is we're going to load this data set that we've seen before, the min wage data set, and we will compute the proportion of those fully employed before and after the increase in the minimum wage, both for Pennsylvania and New Jersey. One is fully employed proportion before, fully employed proportion after, and then we will subset one for New Jersey and one for Pennsylvania, which each of those subsets includes those 2 variables that we were working with. The next step is to go through each of those individual kind of identification strategies. The first one is the cross-section comparison, assuming that there is no confounder. And again, our estimate here for the average treatment effect is just the difference between New Jersey, the post minimum wage increase average full employment rate in New Jersey minus the post New Jersey minimum wage increase full employment rate in Pennsylvania. Okay, so again, we can directly compute this estimate as the difference in the averages of the full employment rate, and that's 0.048. So based on this cross-section comparison, the minimum wage increase actually increased full-time employment. Okay, what is the standard error around this? Of course, the standard error in this difference, or the standard error of any sum of random variables, is the sum of the standard errors if those 2 random variables are not correlated with each other. We're making the assumption that they're not correlated with each other. So we have the standard error as the variance of x and j divided by n, the number of observations in nj, and remember the number of the observations were individual fast food restaurants here. And then the same for the variance of x in Pennsylvania divided by the sample size in Pennsylvania. And we can directly compute that. We compute the number of observations as the number of rows in our subsetted data frames. And then we just plug in our formula. We look at the square root of the variance of our full-time employment proportion after the minimum wage increase divided by the number of observations in New Jersey, and the same for Pennsylvania divided by the number of observations in Pennsylvania. And the standard error that we compute is 0.034 approximately. Okay, So that means, how can we compute the confidence intervals? Again, this is now based on the central limit theorem. We take our average treatment effect, we take the point estimate that we have, and we subtract the standard error that we computed times our critical value. For a 95% confidence interval, of course, that's 1.96, and we add the same product to the average treatment effects for the upper bound of the confidence interval, right? Here are the results for 3 different types of confidence interval: one 90%, 95%, and 99%. We could of course plug in these critical values that I showed you in previous videos, but if you want to directly kind of get them in R, you can also use the qnorm command. Again, remember kind of when we talked about probability distributions and using probability distributions in R, qnorm basically provides you the x value for a given for a given quantile in the standard normal distribution, right? So without providing any additional arguments to the qnorm command, this is a standard normal distribution with mean 0 and standard deviation of 1. If we put in qnorm 0.95, that means we're basically getting the x value where 95% of the probability mass is left of the x value, and 5% is to the right of the x value, right? So that means the underlying value that we're getting here, that is basically the critical value for the 90% confidence interval. Why? We're basically only looking at one side, and there's a 5% on the right of that probability distribution. If we want to look at the 95% confidence interval, of course, we have this. I have to move for the camera a little bit. We have to basically look at plus or and minus that x value, so to speak, where on the left we have 5%, on the right we have 5% of the probability mass. So together the probability mass in the center is then 90%, right? So qnorm of 0.95 gives you the critical value for, and this is also why this z is alpha divided by 2. So alpha divided by 2, that's the 95 or the 5% kind of level on both sides, so divided by 2, that implies that this is the 90% confidence interval, okay? Same for the 95% confidence interval. The critical value is for the standard normal distribution at 0.975, which means there's 2.5% right of that that x value in the standard normal distribution. And so if we do that on both, if we take that off on both sides of the standard normal distribution, we have the 95% probability mass within z and minus z, or the critical values that we get out here. And the same, of course, for the 99% confidence interval, 0.995. The same logic applies. We have 0.05 on the left side, 0.05 on the 0.005 on the left side, 0.005 on the right side to get the 99% confidence interval. Right? So we get our confidence intervals for each of those of those confidence levels, and we see that each of those confidence intervals actually includes 0, right? And so that means that we're not very confident to kind of reject the hypothesis that this treatment, this minimum wage increase, had no effect on on full employment. We're going to talk more about hypothesis testing in this context in the upcoming week. For now, the way we can think about this is that there is so much uncertainty around this this point estimate that we're not able to confidently conclude that this the effect in the cross-section comparison is not equal to 0. Okay. Next, we want to look at the before and after comparison. And of course, here there's a crucial assumption. that when we look at only New Jersey, that the only thing that changes before and after the increase in the minimum wage is the change in the treatment, and nothing else changes. And of course, this assumption is a quite strong assumption, since overall economic conditions changed as well. If we're willing to make that assumption, then our estimate for our treatment effect of that minimum wage increase is just the difference between the average employment before the average employment after the minimum wage increase minus the average employment before the minimum wage increase. And we can directly compute this in R by computing the differences in those averages. Okay, how do we compute the confidence interval and the standard error? The same we did it before. We're looking at the variance of our average treatment effect. And again, we have the variance of the sum of random variables, similar to the previous case, where the variance of x plus y is equal to the variance of x plus the variance of y. But now we can't assume that x and y, so that's employment rate before and employment rate after, are uncorrelated. That's what we did previously in the cross-sectional comparison. Now, if we look at this variance of the sum of random variables, we have to add 2 times the covariance of x and y. In the previous case, we were able to kind of leave this out because the distribution or the distribution of employment in New Jersey and Pennsylvania were assumed to be independent of each other, so the covariance was equal to 0, so we were left with the variance of those two. Okay, now we have to take into account the covariance between those two. Okay, similarly, if we have an additional constant that we multiply, this is now just repeating kind of variance and covariance rules. This is equal to a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance of x and y. Okay, so the factor a and b has to be taken into account here in the covariance as well. Okay, now how do we do this for the variance of the average treatment effect in the context of the before and after comparison? Again, we have our variance of the average treatment effect as the variance of x bar for New Jersey plus the variance of x bar for New Jersey. So this is after the minimum wage increase. This is before the minimum wage increase, minus 2 times the covariance in the x bars before and after. Okay. In both cases, the number of observations, of course, is equal to the number of observations in New Jersey. Okay. Now, the way to compute this in R is to, again, compute the variances in our specific measures, x bar before and x bar after. And the covariance can be computed with the covariance command. And again, keep in mind that these all have to be divided by the sample size. And the standard error that we then get is 0.0176. Okay, so that means based on our confidence interval, the 95% confidence interval is again our estimate minus the standard error times the critical value, which we get here just by using Q norm for 0.975. That gives us the critical value of 1.96. And we see again our confidence interval includes 0, narrowly includes 0. So again, we're not quite as confident that this difference that we observed in terms of the before and after comparison is actually kind of a systematic difference that is not due to chance. Okay. Last, we want to look at the difference in difference estimator, and again, keep in mind that the crucial assumption here is the parallel trends assumption. In other words, that the trajectory of employment in New Jersey and Pennsylvania would have been the same, except for the fact that New Jersey introduced the minimum wage increase. If we look at the estimate of this difference in difference, or the difference in difference estimate, we look at the difference between New Jersey and before and after minus the difference between Pennsylvania before and after, and the difference between those differences is then the estimate of our causal effect of the intervention of increasing the minimum wage. We showed before we can directly compute this as the difference in differences in those average outcomes, and the value is 0.06. Okay, so that means ultimately that, again, this is a positive value on the proportion of fully employed after the minimum wage increase relative to the development in Pennsylvania, where the minimum wage was not increased. Okay, so now what is the variance and standard error around this estimate? How can we characterize the uncertainty? Again, we're looking at the variance in our average treatment effect across repeated sampling procedures. And again, here we're looking at a case where the covariance between New Jersey and Pennsylvania is assumed to be 0. So the variance of that sum is equal to the sum of those two variances. But then these variances themselves, of course, have to include the covariance, right? So this becomes a little bit more complicated. We have two variances. We don't have to include the covariance between kind of this sum and this sum, but we do when we compute the variances in here and in here. We kind of refer back to the way we computed this in our before and after comparison, where we have to take into account the covariance between New Jersey after the minimum wage increase and New Jersey before the minimum wage increase. So in order to do this in R, we have the variance of in New Jersey after divided by the sample size plus the variance of in New Jersey before the minimum wage increase divided by the sample size minus 2 times the covariance between before and after in New Jersey, and the same thing for Pennsylvania. And we see our standard error is around 0.045. So again, computing these confidence intervals, we see that they range between minus 0.02 and 0.15. So again, all these point estimates were positive, indicated a positive effect of the minimum wage increase on full employment, but taking into account kind of the uncertainty around those estimates, we cannot confidently conclude that this treatment effect is actually different from 0. In the next week, we'll talk more about, more formally about hypothesis testing and kind of putting an exact probability on how likely it is to observe the estimate that we saw, assuming that the true population parameter was actually equal to 0. Okay, so that's it for inference in experiments. In the next short video, I'm going to talk about inference with normally distributed data, because as I said in the previous videos, we focused on asymptotic properties and basically invoking kind of large sample theorems. That is not necessarily the case once we work with data that are actually normally distributed.